The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Next presentation is going to be delivered by Dr. Adolfo Matamoros from the University of Texas, San Antonio, and it is again in the same topic of evaluating guidelines for the seismic evaluation of structures using case studies. Adolfo?
Thanks, Sergio. So around 2005, 2006, I was fortunate enough to be invited into a group of people where I was part of that group, and you know, it's beginning to be a few years where we're dating ourselves. And the idea was that FEMA 356 was being adopted as ASCE-41. FEMA 356 was built essentially on the best knowledge of the best people that we had at the time, who made very good guesses about what acceptance criteria and modeling parameters should be for different types of elements. But they wanted to make an effort to shift and try to reflect more what the tests indicated. And so in that group of people, we made changes to different elements. I think that the more significant changes were made to the column provisions. Again, in the last code cycle, we made changes again to the column provisions. And so our philosophy has changed, but it hasn't changed uniformly throughout. The calibrations have not changed uniformly throughout. So the impetus of this is I got really concerned about the fact that we were changing certain elements and not changing others. And in reality, we're modeling systems and drawing conclusions about the behavior of a system that may have many of different types of elements within it. And we may be introducing bias in the modeling and bias in the result by the way in which we have gone about calibrating these modeling parameters and acceptance criteria. So ASCE-41 is, and most of you, I imagine, are very familiar with it. We prescribe in nonlinear analysis modeling parameters that define the curve maybe in the upper left. And we create a mathematical model of the structure, which then we choose a performance objective and a seismic hazard, and then we obtain the results and we compared with acceptance criteria for the different types of elements. We wanted to evaluate that, and the one methodology that is out there to evaluate seismic codes is the FEMA P695. It's really not meant for rehabilitation, but it is a methodology that would allow us to approach this in a more objective and statistical fashion, because you're not doing it with a single ground motion. You have a suite of ground motions, and you can compare the results from near fault and far fault ground motion sets. And through this methodology, it's very different from ASCE-41. You subject your structure to a suite of ground motions. You figure out what ground motion causes collapse, and that gives you an idea of what is the collapse margin ratio for that particular structure. So we wanted to ask ourselves, if we take a building and we model it using the ASCE-41 methodologies, and then evaluate it with FEMA P695, what will that tell us about the probability of collapse of that building? The natural choice was the Holiday Inn by Knox building for a number of reasons. It's been instrumented. There's a wide range of records for different intensity levels of shaking. It's advantageous because it has columns, it has spandrel beams in the perimeter frames, it has slab-column connections in the interior frames. And our interest was in evaluating the system and how the nonlinearity is adjudicated between the different types of elements. So it was actually a great thing that this building had many different types of elements in it. So as I was mentioning, the beam has, today I'm just going to present results for the east-west direction, which is shown there in orange. As I said, the exterior frames have spandrel beams and columns. The interior frames have slab-column connections. The interior of the building really is meant for gravity. In the results I'm presenting today, we're just taking symmetry and showing the results for two frames. The interior frame that is consists essentially of slab-column connections, and the exterior frame, which is spandrel and column frame. So we use zero-length plastic hinge model in which we assign plastic hinges for columns and beams in slab columns, following the recommendations for ASCE-41, modeling parameters in ASCE-41. And the figure on the right shows a typical result from a nonlinear analysis simulation, where you see the orange curve shows the envelope that was built using the ASCE-41 provisions, and then blue shows what the OpenSea's analysis would indicate for a typical run that would follow the simulation or the envelope curve. So having done that, we did thousands of nonlinear analysis simulations. We tracked in each one, so you see the hinges have different colors that essentially is kind of like what Laura and Sun have shown. They're color-coded to show the level of damage. Red is the most severe, green is the least severe. And this particular simulation has been to the point where the building collapses due to lateral instability. And so we do these type of simulations all the way up to where we reach this point. And then we end up with a wealth of information for each of the earthquake ground motions that we run this for. So as I was mentioning, we have a suite of 4 ground motions. Those ground motions we scale to MCE according to the P695 procedure. Fortunately for us, the MCE is about 1 G for the size of the building, so that makes the numbers really easy to interpret after the fact. And for each of those earthquake ground motions, we do an incremental dynamic analysis where we extract the condition of every hinge for each of the nonlinear simulations. Typically, you would end up with curves like these. This is a very brittle building, so you would have a fairly stiff response until the instability hits the building. The columns or the slab column connections are very brittle, and so you get all of a sudden a very flat response. And actually, that's a part that it is quite hard to simulate. It took us a lot of time to be able to get to that point. So when we look at the results, again, this is done in a statistical way. We aggregated all these analyses to develop fragility curves. The curve on the lower left shows a comparison between envelope using ASCE-41 13 and ASCE-41 17. And this is done for one of the columns in the building. And the illustration there shows that when we introduced the changes into ASCE-41 17, the goal was to develop modeling parameters for columns that would be reflective of mean response. That was a change from ASCE-41 13 and the work that was done in the addendum, whereas in the addendum we were trying to get conservative estimates with low probabilities of failure, 35% for shear and so on. So our columns move decisively to the right. They're able to deform more without precipitating the collapse of the building. And so when we look at the overall response of the building in terms of lateral instability, and this is a somewhat flawed analysis, because what we do is we allow elements to remain past the point where they lose axial capacity. They just keep going on toward the right with zero stiffness. So if we get past that, what our results were telling us is that as we introduce the change from 13 to 17, the curve moved to the right. That means the probabilities of collapse went lower. To look at the yellow line, in terms of 50% probability of exceedance. We went from about 0.7 intensity measured to about almost 0.9 intensity measured. So that means that whereas ASCE-41 13 would say it takes 75% of MCE for this building to reach lateral instability, ASCE-41 17 would say that it takes about 90% of MCE for this building to collapse. On the red side is what we see with Northridge. I think these curves are interesting in of itself because it gives an idea of what these codes are saying is the probability of collapse of the building. And what I would like to remark about Northridge is these simulations tell us that the probability of collapse under the Northridge earthquake for this building are fairly low, or a ground motion with the intensity of the Northridge earthquake. We looked at the same comparison in terms of acceptance criteria. This is a more restrictive evaluation because acceptance criteria are tied to element behavior, so you can get collapse of the building because one of the columns cannot carry axial load anymore. In brittle buildings like the Holiday Inn, is going to happen before the building reaches lateral instability. So you see the probabilities of collapse drop, and so whereas before we were talking about 75% or 85% of MCE to reach a 50% probability of exceedance, here these are much lower. They're in the range of the 50 and 60%. We see the same pattern though when we look at acceptance criteria for columns is that when we change from 13 to 17, the intensity measures associated with collapse went up, or the probabilities of exceeding went down. The building is less likely to collapse due to column failure under the 17 provisions, that is, under the 13 provisions. The one slide that really got our attention is we get column acceptance criteria. Let me just cut to the chase. Is this one. This shows a comparison between what happens in the columns, or what happened in the columns versus what happened in the beams. So the graph on the left, this is again in terms of acceptance criteria, shows fragility curves for the 13 and 17 editions of ASCE-41. And so our columns move slightly to the right, meaning the larger deformation capacity of the columns meant that if we judge the building on the basis of the columns, then things got better, got slightly better. Right? We're still at about 60% of MCE, so it would mean that for the Northridge earthquake, we were really close to collapse, but not quite there, which is about right for this building. I think that means the ASCE-41 is providing a very decent assessment of what's happening in the building. Now, what's somewhat alarming to us is the fact that if you look at the beams, the curves went in the other direction and moved over to the left. And so that means the probability of reaching severely damaged states in the beams went up as a result of the change in the provisions. We reallocated the damage from the columns to the beams, and the beams are not that important, but perhaps we all would be most concerned about the slab-column connections in the interior, which if you make your columns stronger, then your slab-column connections are the ones that are going to begin to control the collapse capacity of the building. So having seen that, and this is one of the efforts that we're going to talk about a little bit later when we talk about ASCE-41 and what we're doing in the next code cycle. We went and looked at test data, trying to look at those parameters for beams. One, I'm going to show a couple very quickly. So for example, one of the critical points or the response of these collapse analysis is point C, is where we lose lateral load carrying capacity. has a profound effect on when the building begins to become unstable. And we looked at a group of tests performed with elements with low axial load to zero axial load. The log normal distribution shows the distribution of that particular point, where we trace the backload relationship and the point where there was loss of lateral strength. On the horizontal axis, we have the drift ratio. On the vertical axis, we have the cumulative occurrence of that particular drift ratio. And I have two boxes, one in orange and one in blue, that corresponds to values in ASCE-41 as they are today. And so, if we're really attempting to portray the mean response of beams, we would like for those two boxes to occupy most of this graph, so we would like them to be wider, and we would like them to be centered at around the 50% case, which is a drift ratio of approximately 4%. Right now, ASCE-41 has two categories of beam, compliant and non-compliant. For non-compliant beams, the values in ASCE-41 range between 5 and 27% of the drift ratio of lateral load loss for this data set. And in the case of compliant beams, our range is between 16 and 40%. These numbers are extremely conservative, and they're inconsistent with what we have today in the columns, where we would be tracking at approximately 50%. The same goes for, we did a similar comparison for the descending slope. And here it becomes more difficult because the number of data points is smaller and the scatter grows significantly. And we've done work at UTSA with trying to define this parameter for columns, and I think our results are consistent. We see the scatter increase. It becomes harder to define this, whereas the other points you can define much more precisely. But the idea is the same. The larger the number, the steeper the slope. And what you see is based on parameters B and C or E and D of the ASCE-41 provisions, you get much steeper slopes than you get based on the test data. So not only are we estimating the corner in a very conservative way, but this slope is being right now estimated much steeper than we see from the test results. All of that is contributing to the fact that I think we're introducing bias in our nonlinear analysis. So to conclude, this particular building is a brittle building, and we reach collapse. It's controlled by the elements. It's not controlled by lateral instability. And that happens at much lower intensities than it would for lateral instability. So we think on the basis of this analysis that a building like this will experience collapse due to local element failure around 60% of the MCE. In terms of columns, the fragilities between ASCE-41 13 and ASCE-41 17 show similarities with slight increase in the collapse prevention limit state for the columns, and that's in no small part because there was maybe the greatest difference that was introduced was at point B, where we had loss of axial load capacity. This is a personal opinion, but I think it's better to have a greater gap between LS and CP. So I personally see this as an improvement. And I think is more consistent maybe what you might expect with the different performance levels that are defined in ASCE-41. The performance, and I should make a small correction to that, is controlled by beams. Beams in that case can be an interior slab-column connection or an exterior spandrel. We made no difference in the results that we showed you today. If it is a case where the building is being controlled by a beam, we can't tell with a straight face an engineer that they need to go and retrofit their building because their beams are doing bad. So I think we need to reflect that in the way that the assessment methodology is implemented. Again, I think it is clear from the curves that the changes between 13 and 17 lead to profound changes in the probabilities of collapse of the building and the distribution of nonlinear results. And that's particularly a concern in 2017 provision because all the nonlinearity went to the beams, and actually we saw reductions on the demands on the columns. So that's something that is, again, food for thought, and I think driving the efforts in ASCE 369 now to update all of these element modeling parameters so we can obtain a more objective measure of how the damage is allocated within these buildings. There you go.